This is lesson 1 for AP Physics C, mostly dealing with accelerations, velocities, and displacement graphs, and a little bit on free fall. We're going to get started with the difference between distance, displacement, speed, and velocity. Distance is not a vector, therefore it does not have direction. It definitely can be positive, and actually must be positive, because it can't be negative. There's no direction associated with it. So you can think of distance as being the absolute value of displacement. Displacement, on the other hand, has a direction because it is a vector. It can be both positive and negative. And we'll see the same thing for speed. Speed is not a vector, so it does not have direction associated with it. It can be positive, and again, must be positive. It's like the absolute value of velocity. So it can't be negative. Velocity is a vector, therefore it has direction, can be positive, and can be negative. So those are differences between them, and always remembering that concept that we will be plus and minuses with displacement and velocity, but not distance and speed. Look at an example here. An object goes 10 meters east in 2 seconds, 4 meters west in 3 seconds, and 12 meters east in 4 seconds. What's the total distance traveled? I'll take 10 plus 4 to get 14, and add 12 to that. That's going to give me 26 meters. Total distance, we just keep adding it up, and it never goes negative. But what about an object going east, west, and then east again, total displacement? Well, I've got a positive 10 here. I'm going to subtract 4 from that to get 6, and then add 12 to get 18. And then when I'm done, I'm going to write 18 meters, and then east. Notice how I have not associated any direction with this one, but I have with this one here. What's average speed? Well, average speed, then, I'm going to take the 26 meters, and then I'll divide by the total time. We have 2 seconds, plus 3 seconds is 5 seconds, and that's a total of 9 seconds. So to calculate that, I would take 26 meters divided by 9 seconds. For average velocity, I'm going to take 18 and then divide that by 9. Okay, and I see that that's going to be 2 meters per second. When I get done with that, I'll write east, because I have to associate a direction with that. When I divide this one out, I don't have to write anything associated with that at all. So that's our difference between velocity, displacement, and corresponding speed and distance. Now our next topic is going to be on average velocity. In AP Physics 1, we were just given a formula. In AP Physics C, we will derive all of our equations. But let's review a little bit of calculus. If we have a function x of t over an interval from t1 to t2, what's its average velocity? Well, from calculus, the average velocity of a function from a to b is given by this. Average value equals the integral from a to b of f of x dx divided by b minus a. And that is the average value for a function over a given interval. So how do we apply that to velocity? Well, velocity average will then equal the integral from t1 to t2 of vt dt divided by t2 minus t1. So we have some velocity function of time multiplied by dt divided by the t2 minus t1. So what does that become? Well, v sub t is actually the derivative of x with respect to the derivative of t. So dx dt. So v sub t dt, I'm going to sub in this expression right where I see v sub t. equals dx dt times dt. So that will cross off. So what are we left with? Dx. So V average is equal to the integral of t1 to t2 dx over t2 minus t1. Well, when you take the integral of dx, you just get x, and we'll be over a definite integral from t1 to t2, and then divided by t2 minus t1. So what are we left with? When you plug in the definite integral from t1 to t2, V average then is x t2 minus x of t1 divided by t2 minus t1. And that equals essentially delta x over delta t. And that's an equation you're familiar with from AP Physics 1. Graphically, what does that mean? Well, graphical interpretations is if I'm on this part of my graph here, and let's call that, of course, t1. And then I end up, let's say, right here. And this, of course, is going to be t2. We really have then the slope of the line that connects both of these points together. That's going to be what our V average is. So indeed, it is equal to delta x over delta t. Now in this case, we're using x to represent displacement, which is on our y-axis here. And time, of course, is actually on our t-axis. So please don't get confused thinking x is an x value that's right there. How do we interpret then average speed? Well, average speed then is going to be equal to the absolute value of that integral. So we're going to take the integral of dx from t1 to t2, but we need the absolute value of that because remember, speed is based on total distance over time. So the absolute value of dx over t2 minus t1. So average speed is then just going to be the positive, okay, of that integral. So we'll have the total distance over the change in time. Now graphically, what that means. Well, if I'm taking from t1 to t2 here, and I want the average speed, I'll just use the letter s for that. Okay, I have to think, what's my distance from here up to my max position here? Okay, let's call that d1. And then what's my distance when I go from here all the way back down there? Let's call that d2. So my average speed is really going to be d1 plus d2 divided by delta t. So actually this is a negative here, right? So we have to make the absolute value of that. This one, of course, is positive here. Okay, so that's our difference between average velocity and average speed, on an actual graph. In our next video, we'll do some examples.